What is fat? Here is one example. Those 3 carbon in red, this is glycerol, and that is the backbone that holds the rest of the molecule together. And the 3 long chains on the left are called fatty acids. And it's small difference in the structure of these chains that determine how good or how bad a fat is for humans. So, fatty acids can be short or long, and another important difference is the type, amount, and locations of bonds between the carbon atoms. Some fatty acids have only single bonds, which are called saturated fat, and some have single and double bonds. They are called unsaturated fat. The unsaturated fat can have one or more double bonds as just mentioned, as it also can have 2 ways to arrange every double bond, both carbons and hydrogens on the same side, or hydrogen and carbons on opposite sides of the bonds, and because of that they behave differently inside of us. In general, most unsaturated fat are good for you, while saturated fat in excess are bad. And, as you may have already heard, trans are terrible for our health, even worse than saturated fat, therefore should be avoided. And why they are bad? Basically because it increases the risk of heart disease and metabolic syndromes like diabetes or insulin resistance. Lipoproteins are lipo and proteins, so basically fat. There are 4 main types which differ from each other according to the ratio between proteins and lipids content. So, if you look at this picture, you can understand that the protein content increases from chylomicrons to high-density lipoproteins. Therefore, chylomicrons have a lot of lipids and little proteins, while HDL has more protein than lipids.
When we mobilize fats in our body, we can refer to 2 different pathways, the endogenous pathway and the exogenous pathway. The exogenous pathway is more likely to happen during the day when you eat more often, while the endogenous pathway is more likely to happen on fasting periods, which we could refer to as during the night or during exercise. The exogenous pathway takes fats from diet, and the endogenous pathway takes fats that are already stored in the liver. We're going to go through the exogenous pathway first. First things first is the ingestion of the fat. Digestion starts in the mouth with the action of lingual lipase that starts breaking down the triglyceride. Further in the stomach, another enzyme breaks down more fat. This enzyme is called gastric lipase. Now, the most important enzyme is secreted by the pancreas and acts in the small intestine. So now we're making a zoom in the small intestine where most part of the digestion is done. Pancreatic lipase will split the triglycerols in fatty acids and glycerol. These smaller parts of fat will combine and form micelles, as well as with the bile coming from the gallbladder. Micelles will stick to the sides of the tube and release glycerols and fatty acids into the intestinal cells. After this, they go to the epithelial cells and come out of it as triacylglycerols. It's so hard to say. And come out of it as triacylglycerols again. These triglycerides stick together to form chylomicrons, which are a kind of lipoproteins, as explained earlier in the video. They are made of fat, cholesterol, and other minor things like protein. Once those chylomicrons are formed, they travel to the lymphatic vessels, and from there they enter the bloodstream. HDL is a high-density protein traveling in the bloodstream. So you can see here of which proteins the chylomicrons are formed. It has ApoB48, ApoE, and this HDL in the bloodstream, it's what is going to fix the last protein, ApoC2, to the chylomicron. So this protein acts as an activator of LPL further in the process. So now, all these chylomicrons traveling in the blood are going to be stored in our body. Where? Well, the main storage organ is the adipose tissue. You can see how they enter the adipose cells with the lipoprotein lipase, LPL. It is activated by ApoC2 and allows then chylomicrons to enter the cells. And once in the cell, they are stored in form of free fatty acids. Now, fat isn't only stored in the adipose tissue. It can also go to other organs such as the pancreas and the muscle. Chylomicrons enter through the same transporter as the adipose tissue, LPL. And the pancreas, as well as in the muscle and the adipose tissue, fat is stored in the form of free fatty acids. So these minor storage in pancreas and muscle are called ectopic organs because it's bad to store fat in them, mainly because it will impair their proper function. So you can see that not everything is stored. There are chylomicrons remnants, which are smaller in protein density, which actually travel all the way to the liver. Not to mention that the liver is an ectopic organ as well. So this is the end of the exogenous pathway. And now we're going to go through the steps of the endogenous pathway. As said before, this pathway is using fat not from the diet, but from the liver. So what differs from exogenous pathway is that fat does not travel in chylomicrons, but in VLDL proteins. And earlier in the video we said, and we explained that they carry more proteins than chylomicrons do. So zooming the VLDL, we can see which proteins it contains. It has ApoB100, ApoE, and as well as with chylomicrons, ApoC2 is fixed through HDL. Now, this fat is transported in the blood by VLDL, and it will be used and stored in the adipose tissue mainly. This is for the proper functioning of the organs while in fasting period. So VLDL enters the adipocyte cells, but how? Well, it's the same thing as in the other pathway. ApoC2 activates LPL, so lipoprotein lipase, and allows VLDL to enter and get stored in the form of free fatty acids. So as in the other exogenous pathway, not everything is taken up by these organs. There are LDL particles which are remnants that will be used in the tissues in our body, and they enter the cells. So LDL particles enter the cells through LDL receptors on the membrane. Finally, part of the LDL particles that were not used go back to the liver and are stored in VLDL particles again. So we say that there is a direct reuptake by the liver. And that was the endogenous pathway. So now we briefly explained why it was bad to store fat in certain organs, such as the liver, the muscles, and the pancreas. And this fat, called ectopic fat, we want to know why is it bad, what are the consequences, and what happens if we store too much fat in those organs.
A healthy adipose tissue buffers the daily influx of dietary fatty acids. If the capacity to store dietary fat is impaired, lipid overflow will happen. The lipids will stay in the circulation and will be directed to other organs for storage. Ectopic fat accumulation is the storage of fat in non-adipose tissue sites, and this will cause lipotoxicity, which is a possible explanation for insulin resistance. The liver, pancreas, and muscle are all insulin-sensitive tissues that are used for ectopic fat storage and may cause insulin resistance. For example, ectopic fat storage in the pancreas will impair the beta cell function, and this will lead to less secretion of insulin. And in the muscle, ectopic fat storage will impair the insulin signaling. The location of ectopic fat accumulation determines whether the fat storage is harmful for metabolic health or whether it's not. We will explain this by the example of the pear and apple shape. An apple-shaped person has more visceral fat storage, which is associated with an increased risk of cardiovascular disease. Contrary to this, a pear-shaped person, which is a typical shape for women often, has more subcutaneous fat, which may actually be protective against cardiovascular disease. Weight gain is related to a decrease in insulin sensitivity, but what are the mechanisms behind this link? Obesity induces alterations in adipose tissue function, which are linked to insulin resistance. As a result of weight gain, the size of adipocytes will increase. This is called hypertrophy. Hypertrophic fat cells are less capable of buffering fat. This will lead to that a majority of dietary fat will remain in the circulation. Because of this impaired adipose tissue storage, lipids will overflow into the circulation, so you will have higher plasma-free fatty acid levels. And more fat will be directed to other organs than the adipose tissue, and so they will be stored as ectopic fat. This may induce insulin resistance in cells are less sensitive to insulin because the translocation of GLUT4 to the membrane is inhibited because of the intracellular fat accumulation. Less glucose will be taken up as a result of this. This may cause hyperglycemia, so high glucose levels in the circulation. Because of these high glucose levels, beta cells will produce more insulin trying to reduce blood glucose levels, and they will get tired after doing this for a while. This will lead to less insulin secretion and in the end will result in insulin resistance. Here you see a nice overview of the consequences of the dysfunction of the adipose tissue. A positive energy balance, so when energy intake is higher than energy expenditure, results in adipose tissue exceeding its buffering capacity to store all excess energy in the form of triglycerides. The reduced buffering capacity of the adipose tissue leads to the overflow of lipids into the circulation, and more lipids will be supplied to non-adipose tissue, so liver, skeletal muscle and pancreas, for storage. The ectopic fat storage in these tissues contribute to the development of insulin resistance. So the question that remains is whether diet can reverse the consequences of impaired lipid metabolism. And indeed, adipose tissue dysfunction in obesity can be reversed by weight loss. A reduction in energy intake will result in a decrease in adipocyte size and a decrease in ectopic fat storage, which in turn will lead to improved insulin sensitivity and lipid metabolism.